go. Homework number 12 in dynamics. We're starting rigid body kinematics, and we're going to do some angular stuff. Angular position, velocity, and acceleration. Okay, so the single stage hoist has been designed, and it has this motor connected to gear A that drives gear B, and gear B is attached to this drum D right here, this guy. And the radius of gears A and B are 75 millimeters and 225 millimeters, and the drum is 125 millimeters. And the motor starts from rest and accelerates at a constant 4.5 radians per second squared. And we're going to try to find the velocity of the load C after it has moved 1.5 meters. And we want to find the time required to move the load. So here it is. Here's my written out version of the thing. And what we want to do is kind of work a little backwards. But first, maybe the question is, does the thing go up or does it go down? That's a good question. Well, when dealing with gears and trying to decide which way something moves, I use a kind of an odd mnemonic to try to remember. I put my hand into the gear, right? So if this gear is rotating clockwise, and first off, this gear has to rotate counterclockwise. I put my hand in there, like my hand would get stuck and start getting crushed, right? So that's and so if I'm looking at multi-stage gears, I kind of look at it that way, and I can kind of decide which way one gear is going to move and the other gear is going to move. I know it's odd, it's weird, but it definitely is effective to think about your fingers getting crushed, and then you remember. Yeah. So anyway. So if this is going clockwise, this is going counterclockwise. And if that's going counterclockwise, the load is in fact going upwards, right? So it does go up. Okay, so we want to kind of try to work backwards, I think. And we want to try to figure out because we were given the acceleration of this, right? We got a distance, right? We might want to trigger it and think, oh, I know of a kinematic relationship where if we know the distance and the acceleration, we could find the velocity. Now that applies to angular velocity and translational velocity just as much. So we kind of know that we're going to be able to use an equation that's very much like this, like right here. Right, and we could say delta y, but it has the corollary of, oops, I just messed up. Okay, I think I'm going to use the omega, this designation, right? Right. So we know this. Okay, so we're also going to use relationships where we have velocities and accelerations at points that are on these circles and have them related this way right here. Okay, so I can actually just walk through this I guess maybe I'm going to do this in examples in class. We haven't had the class yet, but yeah, I don't know if I want to write it all down into this paper. I'm just going to write down this right here. I'm just going to show you the solution, and hopefully you can see what the thought process. Hopefully, all right. So I know how far this thing's moving. So now what I'm going to do is I'm going to figure out how many rotations this thing has to make in order to for this thing to move up. So I will say that delta yc is going to be equal to delta theta d times rd. Right, so you can see that this thing, the coil, this rope has to wrap up onto this thing, so we can figure out how many rotations d is going to make. So delta d is going to be that delta yc divided by rd, right? So if this thing has moved up 1.5 meters and we want to divide by the radius of this, right? So it's 0.125. We're going to find out that we have 1.5 and 0.125 divide, and we get that it's going to move up 12 radians. And if you're curious how many rotations that is, just divide that by 2 pi, and that's how many times it has rotated. But we don't really care. We just want to know with radians, right? But now what we want to do, we'll also say that we happen to know that delta B is theta is equal to delta theta D, right? So we know that's 12 radians. Now I want to figure out how many radians, right, has transpired here, right? So on A. So that's just going to be the linear distance that's going on there. So what we could say is RA times delta theta A is going to be equal to RB delta theta B. So we can get delta theta A is going to be RB over RA delta theta B. Or, and we don't have to turn these into meters because they're just a ratio right here. We could say that it's going to be 225 divided by 75 times 12. And what we're going to find here is 225, 75 divided 12 times. So we get that it's 36 radians. By the way, we could have done this a bunch of different ways, so that can make it like a little confusing when working on a problem there, that you can do it in multiple ways. But this is just the approach that seems obvious to me, right? Okay, so we know the delta theta A. We can go back up into this equation and figure out what omega A is going to be. Omega A beginning plus 2 times alpha A times delta theta A, right? So omega A squared is equal to 0 squared, starts from rest, 2 times 4.5 radians per second squared times my 36 radians. And we're going to get omega A is going to be equal to, so we want 4.5 times that times 2 and take the square root. And we get that this is going to be 18, to double check that, 18 radians per second. Let me double check all my numbers here. 4.5 times 2 times square root. Yep, okay. Now that is the speed of gear A when this thing's moved up this distance, but now we need to know the velocity of this. So we kind of going to work backwards into the thing and say, well, we'd want the velocity at the edge or along the perimeter of A is going to equal the velocity along the perimeter of B, right? So what we can say is that RA omega A is equal to RB omega B. So we can find that omega B is going to be equal to RA divided by RB omega A. Or, once again, we don't need to use millimeters. Don't need to use meters because these are just a ratio here. And 18. So we're going to get 75 times 225 divided. And that just ends up being 6. Right? Did I get that right? I think so. Radians per second. Now we know that omega B, omega D, is equal to omega b, which is 6 radians per second. So, and we also know that the velocity of c is going to be equal to rd times omega d. So that's going to end up being, and we should turn it into meters this time because we want things in meters per second. So we're going to take our 0.125 and multiply it by 6, and we're going to get, so 0.125, we're going to get 0.750 meters per second. I think I did that correctly. And it's going to be upwards right here, because did I ask for velocity or speed? The velocity. So we need to give direction when we give the answer. Now we need the time. Okay, we could do this in any way that we want. We know that all the stuff that right here is all true for whatever time has taken place. So the way that I would approach the thing is we found the did we find the velocity? I'm trying to see if there's an easy way to do this with numbers that we already have, so I don't have to go through this long drawn out process. You know what I think, because we have omega a and we have the acceleration at a, right? So this is the one that I would use. I'd use omega a is equal to omega a at the beginning plus alpha a times t. So we could say that t, and I'm going to go ahead and assume that went to 0, is just going to be omega a divided by alpha a. So we got 36.00 radians per second divided by 4.5. So 36 and 4.5, we get 8 seconds. I feel as though I might have made a mistake somewhere. I'm not feeling good about this. I might pause this and double check it before I confirm. So let me double check, see if I didn't make a mistake somewhere. It's out. So I believe we got it right so it comes out to 8 seconds. So here are the answers. A is going to be velocity of c, 0.750 meters per second, and we have, I don't like my arrow, magnitude and direction, and therefore it is a velocity. And B is going to be t is equal to 8.00 seconds. And let's put a nice little box around these so we can comply with my requirements. All right, so we could do this in several other ways. Mostly the important thing, the takeaway, is that we can use our kinematic relationships, our constant acceleration kinematic relationships, and that we have this thing where we have the velocity or we have the distance. We could also, I didn't use it, we could also have the acceleration. We could also figure out what the accelerations were for these. So let me show you that as an alternative thing, and I won't waste any of my engineering paper. I'll just go and use my clipboard I always have handy with some blank paper here. What we could have done is we could have figured out what the accelerations were for each of these, right? So this thing is accelerating, right, alpha a. So it has an acceleration. We could say that this is acceleration here, I don't know what I want to call it. It's on the end of the thing, right? So we have an acceleration there, and we have an acceleration here. So we could say that that acceleration right there, whatever we would want to call it, I'm going to call it AB, right? Because it's shared between both A and B. It has to be the same tangential acceleration. So we say that there's alpha B. There you go. Right, that they have to be the same acceleration. So we could find the acceleration of B by taking RA, sorry. I'm going to take that and divide it by RB. So RA over RB times the acceleration of A, right? Which would have been A over B was 75 over 225, and this was 4.5. So we could say that we had 75, and it's really going to be 1/3 of it, by the way. Well, 75 and 225. Yeah, okay, 4.5. So it's just 1.5. Radians per second squared. And now we could look at the bucket. We could see that that is also going to be equal to the acceleration, angular acceleration of D, right? So we could say, and then looking at a point on D right here, we could look at what this rope has to be. That's going to be the angular acceleration here times the radius of D, right? So we can say the and we note that's going to be the same as the acceleration of C. So we have the acceleration of C is going to be the angular acceleration there times the radius. So we have 1.5, gosh darn it, times 0.125. Right, so we have 0.125. So we end up getting 0.1875 meters per second squared is what C is moving upwards. Now we know this position and we know this acceleration, so we could have the velocity of C squared, velocity of C original, plus 2 times the acceleration of C times delta y of C. 0 squared to 0.1875, and then we know that it's going to go at 1.5. We get the velocity of C. Should be the same thing. It better be the same thing. Square root. We get 0.750 meters per second squared. So you see we get the same thing, right? And then if we want to, we could also find what the time is right here. So we could say that the velocity of C original plus the acceleration of C times time. So we just say 0.75 equals 0 plus 0.1875 times t, and so 0.1875 divided. Ooh, that's not good. I got 4 seconds. Did I do something wrong here? I did something wrong somewhere. $36. Oh, this is where I did. So someone who stops the video too soon is going to see I used 36 when that is the number of radians. It should have been 18. There you go. And I'm not going to record a video. This is why you try to check yourself with some other method. And so that should be 4 seconds. I felt like I was doing something wrong. Just had a nagging suspicion. So anyway, that should be 4 seconds. You could see that I could have done. It was possible to do it in a different way, right? Just a different thought process. I kind of liked this one better because it was dealing with more angles than anything else. Right in there. Okay. So maybe I'll just go ahead and mention in class that there was an error in the beginning, but I solved it at the end. Maybe.